Assalamu alaikum. Welcome to ASTC. So today we will be starting with our first chapter of mechanics, which is straight line motion. This is lecture 1.1, displacement time graphs. Okay. Now, in our previous video, we went through the introduction to mechanics. We saw how the mathematical modeling helps us to approach a real world scenario and how we can apply mathematics to those situations and retrieve results accordingly. Now, in this chapter, there are some prerequisites uh, to this chapter. The first one is you should be able to calculate the area of rectangles, triangles, and trapezium. So the area of rectangle is length into width. The area of triangle is half into base into height. The area of trapezium is half into sum of parallel sides multiplied by the perpendicular height between the parallel sides. Okay. So for example, you have a trapezium. In fact, the example is given here. You have a trapezium over here, and this trapezium, oops, sorry, this trapezium has two sides. Okay, this is the first side, and the other parallel side is of 7 centimeters. I think this is 4 centimeters, not mentioned here. Okay, now the perpendicular distance between these two sides is 3 centimeters. So the area of trapezium will be half into the sum of parallel sides, which is 4 plus 7, multiplied by the perpendicular distance between these two sides. That will be 3 centimeters. Okay, so the area will be 16.5 centimeters square. After that, the second thing that you must know is how to calculate the gradient of a straight line. So in order to calculate the gradient of a straight line, you must have two coordinates which lie on that line. Okay. So for example, we have 2, 4, that's our first coordinate, and we have 7, minus 1, that's our second coordinate. So these two coordinates, they lie on a straight line. Now we need to find the gradient of that straight line. So we can use the formula y2 minus y1 over x2 minus x1. Okay, so here the formula is applied and we get the answer as minus 1. After that, it says that calculate the displacement, velocity, acceleration, and time using appropriate units. So you should know what are the appropriate units for these quantities. When velocity is constant, then the formulae that connect these quantities are as follows. So our first formula is displacement equals velocity into time. You can also rearrange this equation into velocity equals displacement upon time. So for example, find the displacement of a particle traveling at 3 meters per second for 5 seconds. So this is your velocity, this is your time. So you should be able to calculate the displacement. Okay. Now you might be familiar with the terms distance and speed. Okay. But here the terms that are used are displacement and velocity. So what is the difference between distance and displacement, and what is the difference between speed and velocity? So we shall look at that in few minutes. Then velocity is equal to displacement over time. Okay, you can use the same equation, make, for example, if I need to find velocity, so I'm going to make velocity the subject of the formula and then use this equation. If I need to find time, then I'm going to make time the subject of the formula and then I can find time. So depending on what quantities are given to you, you should be able to calculate the unknown. Then when acceleration is constant, then the formulae that connect these quantities are as follows. Also, you should see that they have given you a condition that when can you use these equations. You can use this equation when the velocity is constant. And for this equation that we are going to see over here related to acceleration, you can use this equation when acceleration is constant. Okay, what is the equation? Velocity equals acceleration multiplied by time. Okay, we can rearrange this equation and we get acceleration is equal to velocity over time. All right, so for example, it says find the acceleration when the velocity of a particle changes from 2 meters per second to 10 meters per second in 12 seconds. Okay, So here you have change in velocity, okay, and how much time did it take for that change to take place? That was 12 seconds, okay. So therefore, the acceleration is going to be rate of change of velocity, which is change in velocity divided by time, and that gives you 2 upon 3, which is around 0.67 meters per second square. And similarly, you can also find time, okay, by rearranging the equation so that it is velocity upon acceleration. Now, velocity is the rate of change of displacement and is represented by the gradient of displacement time graph. Okay, so let's say that if I have a graph, this is displacement, this is time. Displacement is represented by S. Okay, so this is not speed, but this is displacement. Now, if you have a straight line graph, okay, now the gradient of this straight line will give velocity of that particular body with that is moving at constant velocity. Okay, so what we're going to do is if we have a graph, we can take any 2 points, any two coordinates on this straight line, and then we can find the gradient. That gradient will be equal to the velocity. Okay, the same concept also applies when we have velocity time graph and the gradient is going to represent acceleration of that object. Okay, then distance time graph does not have a negative y-axis because distance is a scalar. So we are going to look at all of these points in great detail. These are just some bullet points that we should know before we jump into this chapter. Okay, so because distance is something that we call a scalar quantity. Okay, a scalar quantity is the one that only has magnitude, that only has size. It does not have direction. Okay, so for example, some of the common scalar quantities are mass, okay, temperature, the distance, the length itself, right? Because we don't really specify the direction. So for example, if I talk about mass of an object, I don't say mass to the right, mass to the left, mass downwards. We don't say that, right? We are only interested in what is the magnitude, what is the size. So if a person is checking his mass, so that would be like, let's say if his mass is 50 kg. So that's the only thing that we're interested in. We don't really care that in what direction is it applied to, right? But in some quantities, it is important that we also take direction into consideration. For example, forces. It is important that I know, okay, if a force is acting, is the force acting downward or is the force acting upward or is it acting to the right or is it acting to the left? Is the force being acted in northeast direction or is it in southwest direction or is it just towards north? So you see, these are directions that I'm giving. So that is what's important in realizing that there are some quantities that also require direction along with magnitude. Those factors or those quantities are called vector quantities. Okay. Now, since distance is not a vector quantity, it is a scalar quantity. That means that we don't really care about its direction. Okay, that is why it does not have a negative y-axis. Okay, so whenever I'm going to draw a graph of distance time graph, so this is going to be my distance and this is going to be my time. However, if I'm going to draw a graph of displacement time graph, then this is what my graph should look like, because this is going to be my displacement and this is going to be my time. Because displacement is a vector quantity, okay, therefore there will be a negative axis. Okay, and again, what is the difference between distance and displacement? Now we'll look at that in a while. Also, these are some formula that you might already be familiar with from your IGCSE mathematics or from O-level mathematics. Okay, average speed is equal to total distance traveled divided by total time taken. Average velocity is equal to total displacement from initial position over total time taken. Now, although this might not be familiar to you, okay, but this is quite similar to this. formula. All right. Now, the first and foremost concept that we must understand is what is the difference between displacement and distance. Okay. Now, there are two things that I'm going to tell you. Okay. And hopefully, you will not be confused after that. Distance is basically how much ground you have covered. Okay. Distance is how much ground you have covered in total. It doesn't matter where I'm moving. Okay, maybe I might come back to my to the point where I started from. So for example, let's say I started from this point. Okay, and now I went over here, then I took a u-turn, then I went all the way back up to this part. Okay, so how much distance did I cover from this point to this point? That's A. From here to here, that's B. And from here to here, that's C. So I'm going to add up all of my distances, and that will be the distance. All the ground, how many meters I have traveled. Okay, that is the distance. How is displacement different from this? Now, displacement is defined as how far away you are from your initial position. Okay, how far away you are from your starting position. So if I started from here, okay, I travel to the right. Again, I'm traveling a meters. Okay, then I travel upward. I take a u-turn just like in the previous scenario, and then I go all the way back over here. That's c meters. Okay, now for displacement, we don't really care about this part of the journey. Why is that? Because if, let's say, this part of the journey was 10 meters, then that part of the journey is going to be minus 10 meters. Because in displacement, we need to assign a direction. We need to assign a sign, okay, like positive value or a negative value. So usually we use positive value if we are going to the right, and we use a negative value if you're going to the left. So let's say if I'm going to the right, I'm going to say that this is 10 meters. And since I'm going from here to the left, that will be minus 10 meters. So this minus 10 meter and this 10 meter, they cancel out. So now you're over here. Okay. Now, from here to here, how much distance did you cover? So that is what displacement will be. Because if, let's say that, okay, if I just come back over here, okay, let's extend it to this part of the journey in both the cases. So let's say that I stop over here. That's my stopping point. So this was my initial position, and this was my final position. Okay. Now, in case of displacement, we are only going to see that how far I am from the starting position. So this is the only distance that I will be interested in. And since this distance is to the left of my initial position, is going to be minus, let's say minus 5 meters, for example. This is my displacement. Whereas in this case, the distance is going to be A plus B. Let's say this is 10 plus 2 plus 10 plus another 10, and then maybe plus 2. So when you add all of them up, that will be your total distance. Okay, so that is the difference between displacement and distance. So distance and displacement are two quantities that may seem to mean the same thing, yet have distinctly different definitions and meanings. Distance is a scalar quantity that refers to how much ground an object has covered during its motion. On the other hand, displacement, which is represented by S, is a vector quantity that refers to how far out of place an object is. It is the object's overall change in position. Okay. So distance and displacement, if we look over here, it says that when the particle P moves from O to A. So let's say we have a particle, okay, and it starts at O and it moves towards A. Now that displacement and distance, they both will be 3 meters, okay, because they are moving to the right, and the distance between them, between O and A, that is 3 meters. Okay, then when the particle P moves from O to A and back to O, so it starts from here goes all the way up to A, and then comes back to O. Okay, so that will be 3 meters over here and then 3 meters back over here. So distance will be 6 meters. However, displacement is going to be 0 meters because you ended up back on the starting position. Okay, after that it says when the particle P moves from O to A and back past O till it reaches C. So now you started from here, you went to point A, you came back passing from O all the way back to C. Okay, so what happened? From O to A, that was 3 meters, then A to O, that was 3 meters, and then O to C, that was 3 meters. So the distance is going to be 9 meters. However, displacement is going to be minus 3 meters because you went from your starting position towards left, and that was 3 meters. 3 meters to the left. So obviously your length cannot be negative. So when I say minus 3 meters, that actually means 3 meters to the left. Okay. When I say minus 15 newtons, that means that means 15 newtons to the left. That is the direction where the force is acting. So in short, distance is the total amount of ground traveled regardless of direction, whereas displacement is the relative position of an object away from a fixed point. Now, coming to speed and velocity, just like how distance and displacement are different in the sense that one of them is a scalar quantity and the other is a vector quantity, speed and velocity are also two quantities, okay, that are different because one of them is a scalar quantity and the other is a vector quantity. And it's quite easy to remember because S is for speed and S is also for scalar, right? So speed is a scalar quantity that refers to distance an object travels in a given time. Velocity is a vector quantity that refers to the speed of an object in a given direction. Okay, so velocity also takes into account that in which direction an object is moving. All right, so that's about the distance, the displacement, speed, and velocity. Now comes the topic of displacement time graphs. When an object is moving in a straight line, okay, if it's moving on a horizontal road, how can you display that motion in a graphical format? That's done in displacement time graphs. Okay, so a displacement time graph is used to show the motion of a particle in one dimension along a straight line. We first look at examples where motion follows one or more stages of constant velocity, with the particle moving forwards and backwards along the straight line. In displacement time graphs, time t is shown on the horizontal axis. Displacement is often denoted by s and it is shown on the vertical axis. Okay, so this is how a typical displacement time graph looks like. So the y-axis is displacement, x-axis is time. We know that velocity is equal to displacement over time, which can be abbreviated as velocity equals displacement over time, which is s upon t. Okay, so over here, if you notice that I mentioned earlier that the gradient of displacement time graph will give us velocity. Okay, so let's take a look at why is that the case. If let's say that I take two coordinates on this straight line. Okay, this is point A and this is point B. So the gradient will be y2 minus y1 over x2 minus x1. In short, this is change in y over change in x. What was change in y? What is y? Y is displacement. So that is change in displacement, and this is change in time. So do you see we end up with this formula? So that is why the gradient of a straight line, okay, of displacement time graph gives us the velocity of that object which is moving in the straight line. Okay, so this is the formula that is the same as the gradient. All right. Now, velocity is the gradient of the displacement time graph. Okay, so this is your key point. Note that the concept of kinematics or straight line motion refer to the motion of a particle. Okay, if you remember that in our previous video we studied that kinematics is the study of how objects move, right? So it is more relevant to the speed of an object, the acceleration, the time taken, the velocity, and all those factors, right? A particle has dimensions so small compared with other lengths that its position in space can be represented by a single point. Okay, so we can model our object, whatever object is moving, as a particle. Okay, that is our assumption. A body is an object made up of particles. However, in example one, a body, in this case a car, is modeled as a particle for the purpose of the question. So, in order to simplify our scenarios, we usually model the object as a particle. Okay, and once you get the idea of the problem, then slowly and gradually you start factoring in the actual elements. Okay, that okay, if this is a car, then how your model might be tweaked a little bit so that it should give you a more accurate answer. All right. Anyhow, let's take a look at example one. A car moves forward on a straight road from a point O at constant velocity for 20 seconds, traveling a distance of 60 meters. During the next 20 seconds, the car is stationary, remaining 60 meters away from O. The car then returns to O, which takes 10 seconds. Sketch a displacement time graph of the first 50 seconds of the car's journey. So that's the first part of the question. Okay, so you need to sketch a displacement time graph for the first 50 seconds of the car's journey. So if you look over here, there are a few points that we need to underline. That a car moves forward on a straight road from point O at constant velocity for 20 seconds. So starting from the origin, it travels at constant velocity for about 20 seconds, traveling a distance of 60 meters. During the next 20 seconds, the car is stationary, remaining 60 meters away from O. The car then returns to O, which takes 10 seconds. So that makes up a total of three parts of the journey. Okay, so it says a sketch a displacement time graph. So this is how your displacement time graph should look like for the three-part journey. Starting from point O to point A, that's your 20 seconds. Okay, and how much distance was covered, how much displacement was covered, that was 60 meters. Okay, so you're going to draw a straight line from point O to point A, making sure that point A has coordinates 20, 60. After that, it says that the car is stationary for another 20 seconds, right? If the car is stationary, that means the displacement will be the same because the car is not moving. All right, so it is still at a fixed displacement from its starting point. So it is going to remain at 60 meters for the next 20 seconds. So therefore, over here is going to be 40 seconds. After that, it says the car then returns to O, which takes 10 seconds. So now from point B, it is coming back to position O. O means that to its starting position. That means at that point, the displacement should be zero because now you're back to O. Okay. So how much time, what time was it when it came back to O, or when it came back to 0 meters? That was 50 seconds. So you add another 10 seconds to it. So this is the displacement time graph for the three-part journey. Now it says use the displacement time graph to find the velocity of the car during each stage of the journey. So now we need to find the velocity of the car. Just a minute, let me plug in my charger. All right. Now, so we know the coordinates. Okay. So if I want to find out the velocity, so remember velocity is the gradient of the straight line. So I have the origin, which is 0, 0. And then I have point A, which is 20, 60. Okay, so I can use the formula for gradient to work out what the velocity is. Okay, so since velocity is equal to displacement over time, the gradient of a displacement time graph is the velocity. So this will be 60 minus 0 divided by 20 minus 0, which is equal to 3. So the velocity in the first 20 seconds is 3 meters per second. Now Since the car is stationary during the second part of the journey from point A to point B, therefore the velocity is going to be zero. The gradient is zero, so therefore the velocity is also zero. The velocity in the second part of the journey, so over here you have coordinates 40, 60, and 50, 0. So if I use these values, I should be able to calculate the gradient, which will be minus 6. Okay, so now the velocity therefore will be minus 6 meters per second. Now, what does minus represent here? Obviously, speed cannot be negative, right? It means that it is moving 6 meters per second, okay, in the opposite direction to what our original motion was. Okay, so if our original direction of motion was from left to right, the car is now moving from right to left. So that's what negative sign indicates. All right. So the next part is, if you consider a scenario, because this was a pretty straightforward graph, right? So if you are to discuss a little bit more complex displacement time graph, so let's consider scenario between 0 to 2 seconds. P moves to the right 3 units to A at a constant speed. Okay, so it is moving from 0 to A, okay, which is 3 units, and it is moving at constant speed. Then 2 to 5 seconds, P is not moving at all. That means that it is a stationary. Okay, so how can we represent that on our graph? So we only have to consider this part, right? From 0 to 2 seconds, this is our 0 to 2 seconds. The distance covered was 3 units, right? 3 units, so that is 3 meters. Then that was 2 seconds. Okay, so the graph is going to be from point O all the way until this point. After that, it says that from 2 to 5 seconds, P is not moving. Since P is stationary, therefore the distance or displacement, sorry, will be the same until 7. Sorry, my bad. That is 2 to 5 seconds mean that you have to add 3 seconds, right? I thought that was about adding 5 seconds. Then 5 to 6 seconds, P moves to the right 3 units to B at a constant speed. So now if you look over here, from 5 to 6, so this is 5 to 6. It's now moving 3 units to be at a constant speed, right? So you need to add 3 more units. So this was 3. So now adding more 3 units more, that makes up 6 units. So this is where it should end up. After that, it says that 6 to 8 seconds, P moves to the left 8 units to C at a constant speed. Now from 6 to 8, it is now moving in the opposite direction because now it is moving to the left and it has moved 8 units. So you have to come 8 units down. Okay. So starting from 6, you're coming down 8 units. So that will be minus 2. That will be minus 6, right? From 6 all the way, if you go back 8 units, okay, I think there's a mistake over here, should be about minus 2. Okay, from 6 to 8 seconds, okay, it needs to move 8 units, okay, at a constant speed. And after that, 8 to 11 seconds, P is not moving, so again it is a stationary, it is constant. And then 11 to 12 seconds, P is moving to the right at a constant speed. So now since it is moving at the right, that means again the direction has changed. So now it is coming over here, and then it comes to rest over here on the x-axis. So you can pause the video and take a good look at this example. Okay, so this should give you a good idea of how this situation works, right? So on each part of the journey, you have a straight line, right? all of these will have different values of velocity. Some of them will have a positive. So wherever the gradient of a straight line is positive, which is over here and over here, so you will have a positive value for velocity. As for this one, you will have negative velocity because the gradient is negative. Okay, and over here again, you will have a positive gradient. Displacement time graphs show acceleration or deceleration are curved. So far we have seen that how straight displacement time graphs look like, right? Now, when we have straight displacement time graphs, we say that acceleration is constant. And whenever the acceleration is constant, sorry, my bad, whenever we have a straight line displacement time graph, the velocity is constant. Okay, the acceleration is zero, because when the velocity is constant, that means the object is not increasing in speed, and when there is no increase in speed, that means there is zero acceleration. Okay, so those are the points for a straight line graph. How about if I want to show that an object is accelerating? Okay, so when an object does accelerate, then those graphs, those displacement time graphs, are not straight line graphs anymore, they are now curved. Okay, so this is how they look like. Now this shows that velocity is increasing. Okay, now velocity is not constant, the velocity is increasing because you can see that the gradient is not fixed. On a curve, we know that at every point on the curve, the gradient is different, right? And we can see that over here the graph becomes steeper. So that tells us that velocity is increasing because the gradient is also increasing on every point of the curve. All right. And how do we know that the gradient is increasing? We have studied the concept of tangent, right? You might have studied in IGCSE maths or O level maths. So if I draw a tangent over here, so that will be my first tangent. Okay, if I draw a tangent over here, that'll be a second tangent. So you can see clearly that this is a much steeper line, a much steeper tangent, right? So if I were to work out the gradient of this straight line of this tangent, that will be much more than that value of gradient of tangent at this point. Okay, so this displacement time graph shows an object accelerating from rest before continuing at a constant speed. The key is the gradient. Okay, the gradient is the velocity. This displacement time graph shows an object decelerating from constant speed before coming to rest. Now here you can see that the gradient is decreasing. Okay, because at the beginning I have a steeper gradient over here. But then if you, as you move along, you can see that the straight line, the gradient of the straight line, it is decreasing because the graph is becoming less steeper. All right. So that is the end of our first lecture. This was all about displacement time graphs. In our next lecture, lecture 1.2, we will be discussing about velocity time graphs. Okay, this chapter is not too lengthy. It only comprises of two lectures. So the first lecture was about displacement time graphs, the second one is about velocity time graphs. So I hope you enjoyed the video. I'm going to see you in the next class then. Take care.